On November 9th, astronomers encountered something in space that should not have existed according to every established rule of comet physics, and the implications of that discovery continue to ripple outward. A set of razor-straight jets of dust and gas erupted from the interstellar object known as 3I/Atlas, each one maintaining a rigid, unwavering alignment for distances exceeding 1 million kilometers. These structures remain pristine and sharply defined despite the object's confirmed 16-hour rotation period, a fact that immediately placed the observation in direct conflict with everything scientists understand about how rotating cometary bodies behave. Under normal circumstances, jets emerging from a spinning nucleus should bend, blur, or smear into curved or spiral patterns as the source rotates beneath the escaping material. Yet, the November 9th image showed none of that expected distortion. Instead, the jets appeared frozen in space, as if locked to an invisible frame of reference independent of the object itself. This was not a theoretical rendering or an artist's impression. It was a real astronomical image, captured by a major observatory and processed through standard, widely trusted data reduction pipelines. The universe had presented astronomers with something that looked clean, deliberate, and profoundly wrong. The frame from that night shows 3I/Atlas suspended against the blackness of space, its nucleus an unresolved bright core surrounded by an unusually structured coma. From this center radiates a cluster of thin, white streaks, some fanning upward, others extending sideways at sharply defined angles. Each jet is razor-straight, unbroken, and sharply edged, maintaining its coherence far beyond the immediate glow of the coma. The geometry of the scene is anchored by the position of the sun, located off-frame toward the lower left. In that direction lies a broad, faint streak known as an anti-tail, formed when sunlight reflects off dust particles lying between the object and Earth, creating the illusion of a tail pointing sunward rather than away. While the anti-tail itself is not unusual, it stands apart from the other jets, which shoot out in multiple directions and remain perfectly linear over extraordinary distances. None of these jets show the slightest hint of curling, spiraling, or spreading. The field of view spans millions of kilometers, yet the jets hold their orientation with uncanny precision, dominating the image and demanding an explanation that standard physics cannot easily supply. Months before this image was captured, astronomers had already established a critical parameter that would later intensify the mystery. In July and August of 2025, coordinated photometric campaigns tracked subtle rhythmic variations in the brightness of 3I/Atlas. By analyzing these repeating patterns, researchers derived a precise rotation period of 16 hours. This value was confirmed independently by multiple observatories, ruling out spurious signals from background stars or instrumental noise. For a body several kilometers across traveling at interstellar speed, this is considered a moderate to fast spin rate, well within the range of known comets. The importance of this number cannot be overstated. If the nucleus rotates once every 16 hours, then any jet tied to a fixed point on its surface should sweep through space as the body turns, tracing out a curved or corkscrew-like path. Over time, this motion should leave a visible imprint on any stream of gas or dust escaping into space. The straightness of the jet seen in November is therefore not just surprising, it is mathematically incompatible with a measured rotation period. The paradox becomes even sharper when the physics of particle motion is considered. Dust particles escaping from 3I/Atlas travel at roughly 400 meters per second, a typical speed for cometary jets. At that rate, reaching a distance of 1 million kilometers requires nearly 2.5 million seconds or just over 29 days. During that time, the nucleus completes approximately 43 full rotations. If a jet originates from a fixed vent on the surface, each rotation should redirect the outflow, producing a spiral or smeared structure that becomes more pronounced with distance. This effect is not hypothetical. Laboratory experiments, numerical simulations, and observations of countless solar system comets all confirm it. Even with steady outflow, rotation inevitably imprints curvature onto a jet. The only known ways to avoid this outcome are if the jet originates exactly at the rotation pole, or if the outflow speed is so extreme that the material effectively outruns the rotation. Neither condition applies here. The jets from 3I/Atlas emerge at multiple angles, not from a single polar region, and their measured velocities are far too slow to erase rotational effects. By every quantitative measure, the jets should be distorted. Instead, they remain straight. When the Gemini Observatory team processed the November 9th post-perihelion data, the reaction was immediate and visceral. Seasoned observers paused mid-analysis, checking and rechecking their work. Calibration files were scrutinized, raw frames revisited, and reduction scripts reviewed line by line. The possibility of image artifacts or processing errors was exhaustively explored and ultimately dismissed. The geometry persisted in the raw data. The jets were real. Their timing made the contradiction unavoidable. Only months earlier, the object's rotation period had been pinned down with high confidence. With that period, the jets simply should not look the way they do. Internal reports labeled the phenomenon an anomaly, a term that quickly spread through professional channels and became shorthand for a problem no one could yet solve. Slack messages and lab notes from that week reveal a mix of disbelief and urgency, as researchers confronted a result that refused to fit within existing models. As the data circulated, various explanations were proposed and systematically weighed against the evidence. One possibility was that 3I/Atlas had somehow slowed its rotation dramatically, reducing the smearing effect. However, cometary outgassing typically spins objects up, not down, and the earlier light curves showed no indication of a sudden change in rotation rate. November observations did not suggest a sluggishly rotating body. Another idea involved sunlight trigger jets, where gas erupts only when specific surface regions are illuminated. Yet this model predicts a series of discrete puffs spaced along the jet, corresponding to each rotation. Given the travel time of the dust, the November image should show dozens of evenly spaced knots, not continuous, unbroken lines. The fragment tail hypothesis suggested that small pieces had broken off near perihelion, each producing its own straight tail. But there was no evidence of a breakup. Light curves remained stable, and no high-resolution images revealed a swarm of fragments. The nucleus appeared intact. The most speculative idea, kept deliberately at the bottom of the list, invoked controlled, thruster-like jets analogous to spacecraft propulsion. Few scientists embraced this explanation, and most assigned it a probability well below 1%. But some argued that if all natural models fail, even uncomfortable possibilities must remain on the table. Compounding the mystery is the object's extraordinary orbit and composition. 3I/Atlas travels on a path almost perfectly aligned with the ecliptic plane, but in a retrograde direction, moving nearly opposite the flow of the planets. Its inclination deviates by less than 5 degrees from Earth's orbital plane, a combination that is vanishingly rare among known interstellar visitors. Its size, estimated between 1 and 5 kilometers across, makes it larger than Borisov and vastly larger than Oumuamua. Its hyperbolic excess velocity exceeds 23 kilometers per second, placing it at the high end of known interstellar speeds. Spectroscopic observations from the James Webb Space Telescope and the Very Large Telescope reveal a coma rich in nickel, but strangely poor in water, with water vapor making up only about 4% of the mass. Most comets are dominated by water ice. The nickel-to-iron ratio measured in the plume is orders of magnitude above solar system norms, another statistical outlier stacked atop the rest. Laboratories around the world attempted to replicate the jets under controlled conditions. Spinning ice-dust mixtures in vacuum chambers, researchers consistently produced plumes that twisted, blurred, or fanned out, never maintaining the razor-straight geometry seen in space. Simulations tweaking surface roughness, outflow speed, and thermal properties all failed to reproduce the observations. Even speculative ideas involving magnetic fields guiding the dust found no supporting evidence. As replication efforts stalled, attention turned back to the data itself, and tensions grew within the scientific community. Telescope time